Hello everyone. In this lecture, we will discuss the notion of orthogonality in an inner product space. The other term that we use for orthogonal is perpendicular. So the question is, when can we say that the two vectors are perpendicular to each other in an inner product space? Now, suppose I have two vectors, say x and y, in an R2 plane or maybe in an Rn plane. We know the relation between the dot product and the angle between these two vectors. So it's given as x dot y as norm of x into norm of y cos of theta. Now as we know that this dot product is the standard inner product, and considering this dot product in Rn, we generalize an inner product in the other space. So first of all, we will see what is the condition that is required so that this vector are perpendicular to each other. Definitely this theta have to be 90 degree, and if this theta is 90 degree, in that case x is perpendicular to y. In other words, we say that in the language of an inner product space, we call that this x is orthogonal to y. Okay. So if this theta is equal to 90, then definitely this cos of theta is going to be 90 degree, then cos of theta is going to be 0, and so the inner product or the dot product or the scalar product of this x and y will be 0. So this is what we generalize. Okay. As we know that this is the standard inner product in Rn, we say that any vector x and y in an inner product space are orthogonal to each other if their inner product, whatever the inner product that is defined, is 0. This is a value in f. So if this is equal to 0, then we say that x is orthogonal to y. So that's why we have this as the definition of x is said to be an orthogonal to y. So given a two vector in an inner product space, say x and y in V, then x is said to be orthogonal to y if inner product, this is the necessary and sufficient condition for x and y to be orthogonal, if the inner product of x with y, that is this bracket x comma y, is equal to 0. Okay, in fact, we can talk about the orthogonality of vector to some subset of an inner product space. So x is said to be orthogonal to S, where S is some subset of V, if x is orthogonal to every element of S. Basically, this means that is what I mean to say that x is orthogonal to S in V if and only if x is orthogonal to every element of S. That means if you take the inner product of x with any element of S, then this has to be 0, and this should be true for every y in S. Let's take one example here, a simple example of in Rn. So consider inner product space Rn or R3. So let me take S to be the set 1 comma 0 comma 0 and 0 comma 0 comma 1, and let x be a vector, uh, say 0 comma 1 comma 0. So when I don't mention an inner product, that means that we are discussing a standard inner product space. Okay. So now you can check that this x is orthogonal to both these vectors of S. How would you check? I'll check x dot with 1 0 0, which is same as 0 comma 1 comma 0 with 1 0 0. And in fact you can see the geometrical interpretation of these three vectors. 1 0 0 lies on x axis, 0 0 1 lies on z axis, and 0 1 0 uh, lies on y axis. So definitely all these three axes are perpendicular to each other. So in fact, even if I uh, take the inner product, I mean if I take any of this as my x, okay, and if I put this in S, again that x will be orthogonal to every vectors of S. Okay, so let's check it out. Dot product. How the dot product is defined? This into this, 1 into 0, 0 into 0, which is same as 0. Okay, so x with this is 0. Next I'll check x, the dot product of x with this 0 comma 0 comma 1. This is basically, as per the definition, the inner product of x along with this vector 1 0 0, and this by definition inner product of x. So this is one simple example. So here once again 0 1 0 dot with 0 0 1, and so you get 0 into 0 plus 1 into 0 plus 0 into 1 is equal to 0. So that's one simple example. So therefore I can say that x is orthogonal to uh, S. Okay, if you want an example of two orthogonal vector, then in that case you can take this y as 1 0 0. You can see that x dot y is equal to 0, so therefore x is orthogonal to y, as well as x is orthogonal to this particular vector. So that would be one example. All right. So since you might be looking for this definition for the first time, I want you all to take a pause, review what we have discussed, and then you can proceed. You can pause the video in between any time. Okay. Now here one thing we can immediately note down. First thing, from the properties of an inner product space. In any inner product space, see what happens if x comma y is equal to 0. By definition, this means that x is orthogonal to y. From here, can I say that y is orthogonal to x? Okay, so for that, I have to have this y in the first position. So how do I convert this? I know that x comma y can be written as y comma x and its complex conjugate. So or basically uh, I'll simply take the complex conjugate on both sides. This becomes 0, right? But 0 conjugate is as same as 0, and you know that this is same as y comma x is equal to 0, right? This here denotes a complex conjugate. Now this says that now y is also orthogonal to s. Okay, so I can make a note that if x is orthogonal to y, then y, I can say that y is orthogonal to x. So it doesn't matter whether you say x is orthogonal to or y is orthogonal to x, it means the same thing. The second thing that you should observe is that from the basic properties of an inner product space, of an inner product, if I consider the inner product of any vector with 0 vector, this will always be equal to 0, which means that every vector is orthogonal to 0 vector. Okay, so this means that every vector in V, every vector in an inner product space is orthogonal to 0 vector, right? As per the definition of orthogonality. Okay, let's move on to the more general definition of so-called as an orthogonal set. Suppose I have a set in V, say S, then when can I say that this S is orthogonal set? If every distinct element in S are orthogonal to each other. You get it? So suppose S have say some elements, then what I'll do to check whether S is orthogonal or not, I'll check for the inner product of every distinct pair. If all this inner product is equal to 0, then I say that S is orthogonal. And using quantifier, how can I write down, or using mathematical notation, how can I write down this? S is orthogonal. Suppose this should have been S is an orthogonal set. No problem. If and only if, what happens? X comma y is equal to 0 for every x and y in S, with one more condition, that is x is not equal to y. That is because we are, as of now, we are not talking about that set where the inner product with itself is also equal to 0. We are not considering that. Okay, so we will check for the inner product of every distinct pair in S. If that is equal to 0, then we say that the set itself is an orthogonal set. Uh, one quick example that we can produce here is that just an extension of the previous example. If I consider S equal to a standard basis of R3, 1 0 0 0 0 1 0 0 0 1. Okay, this is one example. In fact, this 1 can be replaced by any other quantity as well, because see what happens in this case. Where does this, let's see the geometrical representation. Say 1 0 0 will lie here, right? This is z-axis, so 0 comma 0 comma 1 will lie here, and uh, this 0 comma 1 comma 0. You know that the angle between all these three is 90 degrees. So for that matter, in fact, you can take uh, any point, any 3 points lying on this x-axis, they will always be orthogonal to each other. So even if we take say some other 3 choices lying on this x-axis, y-axis, z-axis, then again it would form an orthogonal set. So that is an idea. See, if I take 9 comma 0 comma 0 somewhere here, then if I take 0 comma 0 comma say 5, and if I take a point over here, say 0 comma 10 comma 0. Okay, so again this set of point will also form an orthogonal set in R3. Okay, so not always you may take a points lying on x, because these are the standard points, the points which are lying on x-axis, y-axis, z-axis. Again you may take a point lying like this. Okay, so that would also form an orthogonal set. So only thing you need to check whether the dot product of every distinct pair of that particular set is equal to 0. In this case, as the dot product is the standard inner product from R3. Okay, so once again you can just review what we have done so far. That is the definition of orthogonality of two vectors, then the definition of an orthogonal set in terms of its inner product. Okay, so the first property which we'll be discussing here is that every orthogonal set in an inner product space not containing the zero vector is linearly independent. So now it is clear to you why we want a set, orthogonal set not containing a zero vector, because if it contains a zero vector, then it won't become a linearly independent set. It might be an orthogonal set, but it won't be a linearly independent. Okay, before this, before proceeding with the proof of this, we will recollect the definition of inner product linearly independent set. So in fact, we have defined this previously, linearly independent set, but here we will talk about infinite linearly independent. So when do we say an infinite set a linearly independent set? Okay, so an infinite set, because the given set may be an infinite set. So in that case, how would you check whether it's linearly independent or not? So in infinite set is said to be linearly independent if it's every subset. So what you will do, you will check for every finite subset of this set. If the definition of the linearly independentness hold for every finite subset of this infinite set, then you say that the given infinite set is also linearly independent. So if it's every finite subset is linearly independent. Okay, so the definition we required here, because the given, to prove this, because the given orthogonal set may be an infinite set also. So we will discuss this in case wise. In fact, one case is enough to uh, show that the every orthogonal set in an inner product space not containing zero vector is linearly independent. So the first case that I'll take is that I'll consider an infinite uh, orthogonal set. Okay, so let inner product space, let this be an infinite orthogonal set not containing zero vector, or I can also say that this is an orthogonal set containing non-zero vectors. Okay. So how would I show that if it's an infinite set? How would I show that it's a linearly independent? I'll have to show that every finite subset of this S is every finite subset of this S is linearly independent. So how do I show that every finite subset of S is linearly independent? So I'll choose in random any arbitrary finite subset of this S. So let S1 containing say n vectors, say x1, x2 till xn, be any finite subset of S. Okay, so we will show that, okay, finite subset of S. So definitely, since this is a subset of S, it won't contain any zero vector, right? And also, since S is a orthogonal set, by that we mean that the inner product of every distinct pair of S is equal to 0. So definitely if I look at every distinct pair of this S1, that will also be equal to 0. Okay, So if I consider x1, say suppose let xi comma xj belongs to S, where I comma j is coming from the set 1 2 till n, and I is not equal to j. So definitely if I is not equal to j, xi won't be same as xj. Okay, if I consider this as the set of distinct element. Okay, or I would say that, rather I would say xi not same as xj. Okay, s1. Now since s1 is a subset of S, this xi comma xj will also belongs to S. And being this S is an orthogonal set, the inner product of xi comma xj will be equal to 0, as S is an orthogonal set. So these are some arbitrary element I had chosen from S1 which are distinct, and I have shown that their inner product is equal to 0. Therefore S1 is an orthogonal set not containing 0 vector. So now my aim is to show that this S1 is linearly independent set. So I'll write down the claim S1 is linearly independent in V. So how do I show that certain set is a linearly independent set? I'll consider the linear combination of this particular vectors equal to 0, and I'll show that the only scalars associated to is are 0 scalar. Okay. So let alpha 1, alpha 2, and this goes on till alpha n be a scalars such that alpha 1 x1 plus alpha 2 x2, and this goes on till alpha n xn is equal to 0, right? So I'll consider this equation as the first equation. Now I have to show that each of these alpha, this implies that each of these alpha i's, that is alpha 1, alpha 2 till alpha n, are 0. Okay, so how do I show this? The only fact that I know is that the inner product of xi with xj for any I and j coming from 1 to till n with xi not same as xj is equal to 0. So I have to use that fact to show that each of these alpha I is equal to 0. Well, so what we do here is that now I'll fix one such suffix which is varying from 1 to n. So I'll fix it as k. Say fix k from. So it will be either 1, 2 till n. Now as of now what I'll do is that with this process I'll show that corresponding to this k, its alpha k is equal to 0. And by using the same process for the rest of the elements in this set, I can show that all such alphas are equal to 0. Okay, so for this fixed k, I'll consider this particular inner product xk comma 0 vector, right? One thing also I should be taking care here, this is an vector xk comma 0 vector. We know that this is equal to 0 by the property of an inner product, but as of now I can replace this xk by this whole equation, right? Because I know that in V 0 is also same as this, right? So I can replace this 0 as alpha 1 x1 plus alpha 2 x2, and this goes on till alpha n xn x equal to 0, right? So this is what we get from 1. All right. So in fact this is going to be xk comma alpha 1 x1 plus alpha 2 x2, and at the kth position you will have alpha k xk, and this will go on till alpha and xn. Now that k might be 1, that might be n also. Okay. So now let me use the properties of an inner product to split this. Okay, now how can I split this? See, we know that inner product of x comma y plus z is same as x comma y plus x comma z. Now can I extend this property for finite vectors instead of having only sum of two vectors here at the right hand side? So it's going to be x comma y say plus z plus say u. Can I write down this as x comma y plus x comma z plus x comma u? That's possible because at first stage you consider this as y plus say this vector z plus u. Using this property you will have x comma y, and then you will have x comma z plus u. Now you can split again this using this property, so this will become x comma y plus x comma z plus x comma u. So we can extend this for any finite sum. Okay, so not only for the sum of two vectors. Okay, and because of that I can write down this as xk comma alpha 1 x1 plus xk comma alpha 2 x2, and this sum will go on till I will also have in between xk comma alpha k xk. Okay, and this will move on till xk comma alpha n xn, this is equal to 0. So what you observe here is that once again I can apply the property to remove the scalars out. Okay, so this would give us alpha 1 conjugate, because this is in the second coordinate, alpha 1 conjugate xk comma x1 plus alpha 2 conjugate xk comma x2, and this goes on till the kth term we will have alpha k conjugate xk comma xk. Okay, this is the rough work, plus this goes on till the nth term is going to be alpha n conjugate xk comma xn. By the way, I just want to make one change here. See, when I say that this is a subset of S, here I consider all the distinct elements. For I not same as j, xi is uh, different from xj. Okay, so I'll make that change. I not equal to j implies xi not equal to xj. Okay, because repeating the same element in a finite set doesn't make sense. Okay, so that can be generalized. Okay, now proceeding further, what you know is that xi comma xj is equal to 0 if I is not same as j, or xi is not same as xj. But when I is not same as j, that implies xi is not same as xj. So when I and j are distinct, we consider that the vectors, the corresponding vectors are also different. Okay, so therefore what can you say about this inner product? This is going to be 0, right? Because that set is an orthogonal set, and you are taking an inner product of xk with x1 and not with xk. So this also here k is not same as 2, if at all it is same, because we are considering it is somewhere in between. If it is k is equal to 2, then this is going to be a non-zero. Okay, so this will be 0, and we assume that this k lies in between somewhere. Then for this only we are going to have a non-zero quantity. If you remember uh, the relation of an inner product with the norm, this can be written as norm of xk the whole square. and since xk is non-zero, this will always be a non-zero, right? This term, the next term will also be equal to 0, alpha k plus 1 conjugate into 0, and like this sum go on till the last term will also be equal to 0. So what do we get from here? This becomes 0, this becomes 0, all the term except the kth term will have, and that is same as alpha k conjugate into norm of xk the whole square is equal to 0. So this is like a product of two terms in f. Now what we know is that each of these xi's are non-zero because S is a set containing a non-zero vector. So obviously S1 will also not have a zero vector. So therefore this should implies that alpha k conjugate is equal to 0. As xk is a non-zero, this implies that norm of xk is non-zero, right? And if the conjugate of the number is equal to 0, the number itself is have to be equal to 0. Okay, so with this process we show that each of these scalars, because by fixing k in this set 1 2 till n, we have shown that alpha k is equal to 0. Okay, now if I vary that k over the set, then I'll show that each of this alpha is equal to 0. Okay, for every I varying from 1 2 till n, which says that the given set S1 is linearly independent. Therefore S1 is linearly independent. Okay, so you can go through everything, review, and then proceed. Take a pause in between, review, and then proceed. So next case obviously is the case when S is finite. When S is finite, in fact that follows from the case 1 that S has to be a linearly independent, because any finite subset of S, we have proved that it's a linearly independent, right? So if S itself is a finite, we can prove in a similar way that S is linearly independent. Okay, from case 1 itself. We don't have anything to prove in case 2. So this proves the important result, which says that an orthogonal set is a linearly independent set provided it does not contain any zero vector. Alright. So now we move on to the next property of an orthogonal set, that is this, which is proved again in a similar way. Suppose I have an orthogonal set, once again containing a non-zero vector, and if y is an element belonging to the span of that orthogonal set, then y is expressed in this way. Basically we know that if y belongs to the linear span of S, y can be expressed as a linear combination of these vectors of S. That is, it can be written as alpha 1 x1 plus alpha 2 x2, and this goes on till alpha n xn. Okay, now if we know that this S is an orthogonal set, in that case I can explicitly find out those scalars alpha 1 alpha 2 till alpha n, and that scalar is given in this. So for I is equal to 1, alpha 1 is nothing but y comma x1 upon norm of x1 square, and this makes sense because each of these xi is non-zero, and therefore norm of xi is strictly greater than 0. It's going to be a non-zero, and therefore this makes sense, right? So let's try to prove this. This is proved again in a very in a very similar fashion. So proof of this, we are given y belongs to linear span of S. This means that y can be written as alpha 1 x1 plus alpha 2 x2, and this goes on till alpha n xn for some choice of alpha I in f, okay, where I is varying from 1 to till n. Alright, so as I mentioned to you earlier, that only thing I need to show here is that this alpha 1, I mean this y have to match with this. I already know that y will have this expression. If I compare it to this expression, that is what we want to show, then I have to show that each of this alpha I is of this form, y comma xi upon norm of xi square. Okay, so only thing that this is written in the compact form using this summation. So if you split it, you will see that it is in this form, where you will see that alpha 1 is given as y comma x1 upon norm of x1 square, alpha 2 would be y comma x2 upon, and so on till the scalar alpha n would be y comma xn upon norm of xn whole square. So I have to show this. Okay, so how would I show this? Once again, I'll fix k in this set, and I'll be showing that alpha k, I'll be proving this statement for alpha k. So how do we proceed? We proceed in this way. Okay, in fact, if you look at the claim, that itself gives us a hint. Basically, we want to show, in fact I'll write down, alpha k is same as y comma xk upon norm of xk the whole square. If I prove this, then we are done. Okay, so I'll have to look for this inner product space, inner product, that is y comma xk. So I can compute that y comma xk from here itself, because we have an expression for y. I'll call this as star. Now I'll compute this, and I'll show that this is same as alpha k into norm of xk the whole square, and then we are done. So that is as simple as that. So I know now y from this expression star is same as alpha 1 x1 plus alpha 2 x2, and somewhere in between there will be k, alpha k xk, as that k is varying in 1 2 till n, and this goes on till alpha n xn, right, this inner product with xk. Now we can simplify this further, as you can see that the first coordinate is nothing but the sum of n vectors. So I'll have to split this as alpha 1 x1 comma xk plus alpha 2 x2 comma xk. The second coordinate remain fixed, and this goes on till we will also have alpha k xk comma xk in between. Okay, and this goes on till alpha n xn comma xk. Don't forget the fact that this S is orthogonal set, which means that if I consider the inner product of any two distinct pair, that is inner product of xi comma xj, where I is not same as j, then it's going to be equal to 0. Distinct pair. Okay, so now I have specified k somewhere here. So that means if I simplify this further, then I'll get alpha 1 as x1 comma xk, as alpha 1 is occurring in the first coordinate, then alpha 2 x2 comma xk, and I have specified my k in between here. So if you observe each of this term, you will see that you have an inner product of xk with every other terms of s, every other vectors of s. For example, this is inner product of x1 with xk. Now k I have specified here, that means this inner product have to be equal to 0. Same way this inner product will be 0. The only term that will survive is this alpha k, and by definition this is same as norm of xk square. Okay, and this goes on. All the other term will be equal to 0, right? Okay, so you have alpha k into norm of xk the whole square. Now, why this is the only term that will survive, and this term is going to be non-zero provided this alpha k is non-zero, right? This norm of xk the whole square is non-zero because the set S contains non-zero vector. Okay, and this is the inner product of xk with itself. Okay, so that may not be equal to 0 in an orthogonal set, and that will not be 0 provided that xk is non-zero, and we know that xk is non-zero. So that's it. So what do we have here? From here I can say that y comma xk is equal to alpha k into norm of xk the whole square, which would mean that alpha k is same as y comma xk upon norm of xk the whole square, as xk is non-zero. So that means in this expression that alpha k, the scalar, is y comma xk upon norm of xk the whole square. So in this way I can show that each of this alpha I is of the form y comma xi upon norm of xi the whole square for every I moving from 1 to till n. And therefore from star y can be written as alpha 1, which is going to be y comma x1 upon norm of x1 the whole square into x1 plus y comma x2, that is alpha 2, upon x2 the whole square into x2, and this sum goes on till alpha n, that is y comma xn upon norm of xn the whole square into xn. And this can be written in a very beautiful form, that is in the form of summation I going from 1 to n. Y, you can see what is varying, xi is varying, and down it's varying as norm of xi square into again xi is varying. Okay, so that's why we have y as this. Alright, for today I'll stop here. Please go through what we have discussed in this particular video. You can pause the video in between to review what we have done, and then you can proceed. So if you have any doubts or if you have any queries, then you may discuss in the next online session, and for the attendance purpose you give your attendance in the comment section. Thank you.